All right, let's dive in. Today, we're not just looking at some old math problem. We are heading out on an adventure. A 350-year-long quest that all started with a little note scribbled in the margin of a book.
Can you imagine that? So picture this. It's the 1600s, and this lawyer and hobbyist mathematician, Pierre de Fermat, he leaves this ridiculously tantalizing message for the future. He says he's got a truly marvelous proof for something, but oops, no room to write it down. Just that one sentence. And it kicked off one of the greatest intellectual scavenger hunts in human history.
Well, that's exactly what we're going to do right now. See, this isn't just a story about the past. This is an invitation. An invitation for you to step into the shoes of an explorer, to feel that thrill of the puzzle, and to see mathematics not as a boring subject, but as this huge, uncharted landscape just waiting to be explored. So let's begin where it all started, with the puzzle itself. A puzzle born from that famous and, let's be honest, frustratingly small margin. Here it is. It looks so simple, doesn't it? Kind of looks like something you'd see in a high school algebra class. In this equation, a, b, and c are just whole numbers, and n is the power you raise them to. The whole entire mystery is locked up inside this one elegant little line. Now, here's what's so wild about this. Fermat's theorem isn't about finding a solution. It's about proving that a solution is totally impossible. He claimed that if that little n is any number bigger than 2, so we're talking 3, 4, 5, all the way up to infinity, you will never find 3 whole numbers that make this equation true. Ever. I mean, what a bold claim to make. So, to really get why this is such a big deal, we're going to start with a little warm-up. We're going to tackle the one case where it does work. Think of this as your first quest as a mathematical explorer. Okay, so here's the key. Fermat's rule only kicks in after the number 2. When n equals 2, that equation, a squared plus b squared equals c squared, well, that's just the Pythagorean theorem. And for that, there are tons of solutions. They're called Pythagorean triples. This is our training ground. All right, let's get our hands dirty for a sec. We all know the classic. 3 squared plus 4 squared equals 5 squared, right? That's 9 plus 16, which equals 25. It works. So what happens if you just double everything? Let's see. Is 6 squared plus 8 squared equal to 10 squared? Well, that's 36 plus 64, which is 100. Yep, it works. See? You can actually generate new solutions from old ones. Go ahead and pause for a moment if you want and try to find a totally new one yourself. Okay, training's over. Now for the real deal. Let's see what happens the moment we take that one tiny step up from squares to cubes. And this right here, this is the absolute heart of the mystery. On the left, when n is 2, you have an endless ocean of solutions. On the right, you just change that 2 to a 3 and suddenly, nothing. It's an infinite desert. No whole number solutions exist. Go ahead, try it with a calculator if you want. You can get really, really close, but you'll never get it perfectly. This is the question. This is the puzzle that haunted mathematicians for over 300 years. Why does that tiny little change from a power of 2 to a power of 3 or 4 or 500 just slam the door shut on every single possible solution? The answer, as it turns out, is incredibly deep. To climb a mountain this high, mathematicians couldn't just use the maps they already had. They literally had to invent entirely new tools. And these tools, they are some truly beautiful and powerful ideas. You know, to finally crack this thing, they had to connect these seemingly totally separate worlds of math. They needed tools with these wild names like modular forms and Galois representations. But the master key, the one big idea that finally unlocked the whole puzzle, was something called elliptic curves. And these weren't just new formulas. They were completely new ways of seeing how numbers relate to each other. So this is an equation for an elliptic curve. It looks completely unrelated to Fermat's problem, doesn't it? Well, the absolute genius of the final proof from Andrew Wiles was building a bridge between these two worlds. He basically proved that if a solution to Fermat's last theorem did exist, it would create this bizarre theoretical elliptic curve with properties so strange it just couldn't exist. So therefore, no solution was possible. It's a truly profound and beautiful connection. And you know, this is really a fundamental truth about how science and math actually work.
Wiles was standing on the shoulders of giants, who were standing on the shoulders of other giants. This problem wasn't solved in some single flash of brilliance. It was solved over centuries of collaboration, with each generation building a new tool that the next one could use to climb just a little bit higher. And that whole process of building on the past, it brings us to the most important part of this whole journey, you. The torch is being passed, and your adventure awaits. Let's completely reframe how we think about this stuff. Math isn't about memorizing multiplication tables. It's about being an explorer. It's about finding patterns, discovering hidden connections, and just asking really beautiful questions. It's a creative, living landscape. Sure, Fermat's last theorem might be solved, but there are countless others that aren't. Problems like the Riemann hypothesis or the Collatz conjecture. These are the Mount Everests of our time, just waiting for someone with a fresh perspective, a new idea, a creative mind. Someone just like you. Just think about that for a second. The tools that solved Fermat's theorem didn't even exist when he first wrote his note. So what new ways of thinking, what new mathematical tools will your generation come up with to solve the problems we can't even imagine yet? This, right here, is the key takeaway. For Fermat, the margin was too narrow. But for us, it's wide open. We have computers, we have centuries of knowledge built up, we have a global community connected instantly. The tools are here. The great questions are just waiting for you to come and engage with them. So the final question, it really isn't about Fermat anymore. It's about you. Every great mathematician who ever lived started in exactly the same place you are, just being curious and willing to try. The next great adventure is out there. What will you discover?